Hello and welcome to this episode of Physical Attraction. This episode we're going romantic. I know it's a long shot, but together we could reach the stars. The subject is just going to scrape on the possibilities, the frustrations, and the general wildness of interstellar travel, travelling between the stars. Just occasionally you hear an idea for a scientific project so wild, so wonderful in ambition and exciting in scope, it fills you with a childlike sense of joy and wonder. Very often these astounding ideas, antimatter drives, wormholes, ionic propulsion, they come up when we try to figure out how we can move between the stars. Because space is strange. There's an awful lot of nothing up there, which in some ways means that it's an ideal physical system for experimenting with forms of travel that wouldn't work on Earth, but in other ways means that the things you would rely on Earth can't possibly work up in outer space. So some of these ideas are ridiculous and a little bit unworkable. For example, the idea of a traversable wormhole comes up a lot, but there's always been something of a concern about it. So let's talk about wormholes for a minute. The theory of general relativity is our best theory at present to explain the properties of gravity, and it does so incredibly well to a remarkable level of accuracy with a set of equations called the Einstein field equations. One of the simplest solutions you can come up with for the Einstein field equations and the gravitational fields they'll produce is, in fact, what we know as a black hole. The guy who came up with this, Schwarzschild, did so only a few months after Einstein first published his theoretical equations. He found the solution to these equations that was a black hole. He did so in 1916, by the way, while he was still at the Russian front in the First World War, spending his day job calculating trajectories for the shells. He would die shortly afterwards from a disease contracted at the front, but his famous black hole solution lives on, and the proper name for the event horizon of a black hole is the Schwarzschild radius. So for a long time though, people didn't know that black holes necessarily existed. They were just, for ages, solutions to this equation. For a while, people may have even thought that they were really just a mathematical curiosity. There was a big debate amongst theorists about whether they could exist and how they could form, all this for our black holes episodes at some point in the future. But in the 1970s, we started to observe them indirectly. Obviously, the problem with trying to observe a black hole is, since not even light can escape from it, you can't see it in the traditional sense. So you have to infer that it's there through, for example, its gravitational effects on other things. Yet eventually such a mass of evidence accrued that it was accepted that black holes were real, and it was theoretically understood how they could form. The reason I spent all this time pointing out the origin story of black holes is that wormholes also exist right now as a mathematical solution to Einstein's field equations. That doesn't mean that they necessarily exist, and none have been observed yet. So we don't know if they are a real thing that actually exists in our universe, or something that the laws of physics permit, but that can't actually exist. When I say something that the laws of physics permit, of course what I'm talking about is just the theory of general relativity. In the case of wormholes, you may even need a theory of everything that can unite general relativity, Einstein's theory of gravity, and quantum mechanics to understand how they would behave. Since a wormhole theoretically connects two different points in space and time, there's been a lot of speculation that perhaps you can travel through one, and then instantaneously break the light speed barrier, travelling between these 2 points in space and time. This is what you'd call a traversable wormhole. Now, there are reasons to believe that, bizarrely, any wormhole that did form would be so unstable that it would collapse almost instantaneously. And if it connected 2 points in the same universe, there wouldn't even be enough time for light or anything else to traverse the wormhole and reach the other point. Keeping the wormhole open for long enough would require practically infinite amounts of negative energy. In the case of black holes, scientists knew that there was a physical process, the collapse of stars, that could lead to the density required to make one. But we don't know of any physical process that could produce a wormhole, and in all likelihood it would collapse before we even realised it was there. If no known natural process can make a traversable wormhole, and humans would require some mythical, infinitely energetic, anti-gravity substance to build one and keep its walls open long enough to go through, it doesn't seem likely that you can use one to cut down your commute anytime soon. We all know that being sucked into a black hole involves a rather unpleasant process called spaghettification, where you're stretched out by tidal forces as you approach the black hole into a string of atoms. You die, obviously. So if you ever want to travel interstellar distances, please, please, please don't jump into a black hole. It will not go well for you. So much for science fiction. What about science fact? Interstellar travel is very difficult. Escaping the pull of Earth's gravity is a difficult enough challenge, requiring huge rockets and tons of liquid fuel. You can calculate pretty easily the rough amount of energy you need to escape Earth's gravitational field, using Newton's law of gravitation. It's minus g times m over r, where r is the radius of the Earth, m is the mass of the Earth, the other m is your mass, the mass of the object you want to escape from Earth's gravitational pull, and g is Newton's universal gravitational constant. The Earth's radius is 6,400 kilometres, the gravitational constant is 6.67 times 10 to the minus 11, the Earth's mass is around 6 times 10 to the 23 kilograms, so when I put in my mass, that means I'd need around 375 megajoules. Now this is technically the energy you need to go infinitely far away from Earth, but since Earth's gravitational pull diminishes the further away you get, once you get a few thousand kilometres away, we're talking interstellar distances, you've already done almost all of that work. And since I neglected air resistance and the energy you'd need to go at a certain speed in outer space, this is a big underestimate anyway. So I'd need something like 10 kilograms of petrol, perfectly converted into gravitational energy, to lift me into space. Then you need to take into account the weight of the fuel, and this quickly becomes a problem if you want to send very large objects into space. The actual maths requires you to solve a differential equation, maybe some other time, but the basic point here is that sending stuff into space is expensive and difficult, and you don't want to waste any of that on heavy fuel. In fact, beyond a certain point, you won't be able to launch depending on the fuel you use. So the energy density of the fuel, how much kick you can get for a certain amount of mass, becomes crucially important for the launch. And this is a thing that's familiar in terrestrial situations as well, where we try and defy gravity. It's true that, for example, electric aeroplanes are struggling to produce batteries that have a sufficiently high energy density to allow them to take off without having the battery be more than the weight of the plane. But this is just the beginning of the challenge. The distances involved are simply stupendous. The nearest star to our solar system is around 4.3 light years from Earth. The fastest spaceship ever launched was the New Horizons probe, headed to Pluto. It was launched with an escape velocity of 58,000 kilometers per hour. But this is tiny compared to the speed of light. Light travels nearly 6 times as far in a second than New Horizons did in an hour. At the rate of our fastest ever probe, it would take 80,000 years just to reach the nearest star. Now you can talk about being cryogenically frozen and so on, but if you want to see results that are coming quickly, that's just not going to cut it. We clearly need to go at a considerable fraction of the speed of light for several reasons. If we want our probe to reach the nearest star within a human lifetime, so that our investors don't die before they see the fruits of their labours, then we need it to travel at around 10% of the speed of light, or maybe even better. There's also a philosophical argument that sets a lower limit on the speeds we can use for interstellar travel. It's called the weight calculation. The idea here is pretty simple. Assume that technology is continuing to grow back on Earth. It's possible that your probe will simply be overtaken by a faster one that gets launched later on with more developed technology. After all, if your probe as you currently launch it would take 1,000 years to reach Proxima Centauri, but in the next 50 years you can double the speed of craft, then it's clear that you're better off waiting 50 years and launching a probe that would reach Proxima Centauri in 500 years. That way you only have a total of 500 years of travel plus the 50 that you waited, as opposed to the 1,000 from launching the earlier probe. Now, of course, it will eventually become sensible to launch earlier rather than wait for technology to get even better and lose travel time, but this will likely only happen when we can travel at decent fractions of the speed of light. Once you get to a decent fraction of the speed of light, of course, it's different, because then the differences that you're getting are more incremental. Perhaps it might take 100 years for you to double the speed of your probe, and given that Proxima Centauri is only 4.3 light years away, that's not really a considerable gain. Obviously, right now, we're basically in the time when the weight calculation means that it's almost pointless trying to send something to the nearest star, at least with the technology that we're currently using. If we were going to take 80,000 years to get there with our fastest probe, we might as well wait a few hundred years for Ray Kurzweil singularity, or the end of the world, or, hopefully, better rocket ships. Once you leave the Earth's atmosphere, continuing to accelerate gets even trickier. The more fuel you need to carry on board your probe, the more expensive and difficult it becomes to escape Earth's atmosphere in the first place. Worse still, the faster you get, the more difficult it is to accelerate, thanks to special relativity. To accelerate 1 kilogram from 0 to 10% the speed of light requires 125.8 gigawatt hours of energy. That's already the energy output from a very big power plant for more than a day, just to get a 1 kilogram probe up to the 10% the speed of light. To get that same 1 kilogram probe to 50% the speed of light takes 31 times more energy. This process eventually saturates, so that accelerating a mass to the speed of light is impossible, requiring an infinite amount of energy. The last fraction of a percentage will always require an infinite amount of energy to achieve. So I guess you probably need to make the calculation. Is it worth supplying, say, 10 times as much energy for the difference between 95% the speed of light and 99%? Probably not, because it's a small difference in speeds, really. The problem is that you can see here for interstellar travel, we're not running up against ordinary stuff like air resistance. We're running up against fundamental laws of physics, and they really don't like to budge. That's why you need so much energy. A day's worth of power plant output to get 1 kilogram to 10% the speed of light. Worse still, of course, you can't provide this energy from that power plant in outer space. Liquid fuels, like the kinds that power rockets launching on Earth, are completely out of the question. The best chemical reaction fuel can barely provide 40 kilowatt hours per kilogram. It's clearly not worth taking it into deep space, even when you consider the fact that you would struggle to burn it, of course. Rockets powered by these liquid fuels accelerate in the Earth's atmosphere where they have something to push off, and then essentially coast through outer space. There's no air resistance, so they go at more or less the same speed for a very long time, impeded only by space dust and debris that crashes into them, and occasionally, of course, swung around by gravitational fields. Some of the faster speeds that we have obtained with conventional rockets have cleverly used slingshot effects from these gravitational fields to give them a speed boost. Now, nuclear fuels can do better than your chemical fuels because they have a higher energy density. The nuclear decay of plutonium potentially has 16,000 times more energy density than the liquid fuels, the best propane jet fuels that you could use in an aeroplane or a rocket. Nuclear fusion is even more efficient than fission, but given that our best idea on how to do that will weigh thousands of tons and span many kilometres, it's likely that the apparatus to harness energy from fusion will always, or at least for a very long time, be far heavier than the fuel. So the fact that the fuel has a greater energy density isn't really relevant, when all the apparatus you need for it is taking up all of that mass anyway. You need the whole kit and caboodle to confine the nuclei close together, prevent them from escaping, produce the temperatures needed to ignite a sustaining fusion reaction. It's very difficult to imagine that being more efficient than nuclear fission. Of course, the fundamental reason that you might think about fusion over fission is because fusion converts a greater fraction of the rest mass into energy. For a fission of plutonium, around 0.002% of the rest mass energy is converted into energy. But for fusion of hydrogen and deuterium nuclei, it's around 0.4%. Now, of course, matter-antimatter annihilation, as we talked about in the episode on antimatter, releases 100% of its mass as energy. In terms of the energy density of fuel, you can't get more efficient as long as the energy can be harnessed. Annihilation will still occur in outer space, releasing photons that could provide momentum to a spacecraft. But antimatter has its own problems for use as fuel. It's highly unstable and difficult to contain. If the containment fails and the antimatter ever comes into contact with its matter counterpart, catastrophic destruction will follow. Then there's the issue of directing this tremendous energy into useful thrust to drive the spaceship, rather than just irradiating the spacecraft with gamma rays. If what you get points radiation in all different directions, then you're not getting useful momentum transfer that pushes you forward. Also, although we can produce it in particle accelerators and even make some antimatter atoms for our experiments, it's not exactly a cheap process. Current costs are often quoted as trillions of dollars a gram, and making the antimatter requires astonishing amounts of energy. It's also made in tiny amounts, basically as a byproduct of particle accelerator experiments, where a little bit of it gets captured and studied from time to time. I'm guessing that if you actually tried to start mass producing this stuff, you could find better ways of making it, and maybe you could even do it cheaper than we do right now, but it would probably still cost billions of dollars. Since it instantly annihilates everything it touches, you're not going to find a mine of it anywhere on Earth. To get our 1 kilogram probe up to 10% light speed, we'd need around half a gram of antimatter, but only a few nanograms have been produced in the world so far, and of course, if it costs trillions of dollars a gram, you can see that this is going to be a pretty expensive project. Worse still, it's difficult to imagine how you can contain the thing practically in a probe that's launched out of the Earth's atmosphere. You can confine it with a carefully shaped magnetic field, and as we discussed in our episode on the subject, the record for doing that is around 15 minutes. If some method is develop that can confine it indefinitely, you still need to solve the problem of how you don't destroy your container, or even the whole ship, when you explode a little bit of antimatter to give you some thrust. So there are plenty of engineering challenges here, to say the least. It's for this reason that people are looking at more and more exotic forms of transport to truly cover these interstellar distances. And this is the crazy, wild, imaginative sci-fi project that I wanted to talk about. The Breakthrough Starshot project envisions a fleet made of tiny spacecraft that will be powered and pushed forward by a gigantic array of lasers. I know. And it was this mad project that made me want to write about it in the first place, because people are actually kind of working on it. Now, of course, it's been endorsed by the usual cast of sci-fi dreamers that you find endorsing this kind of thing. Your Musks, your Hawkings, that lot. But how does shooting a whole bunch of lasers at a tiny, lightweight spacecraft actually work? The photons will transfer momentum. Light can give a push to lightweight wings, perhaps made of graphene or some similarly exotic material. And the spaceships, pushed by these photons, could be accelerated to significant fractions of light speed. This gets around the problem of having fuel on board, because what you actually do is just have a huge wingspan for the lasers to push on. And you can theoretically accelerate these lightweight probes to incredibly quick velocities if you have the appropriate set of lasers. But of course it tells you something about how ambitious your project is when you need a vast fleet of lasers all over the Earth to accelerate craft to tens of thousands of kilometers a second in just 2 minutes. I think the theoretical calculations that they've done, if you had the lasers that they were talking about, would enable you to get up to a quarter of the speed of light, maybe more. That's the aspirational goal for this project. Then you start beaming back data at the speed of light from the nearest star. So our probes could get to the nearest star in, say, 20 years and start beaming back information to us. Which means that if this project is actually completed in the next few decades, there's a chance that we might see the first data from a probe that visited a nearby star or planetary system within our lifetimes. Of course, our lifetimes might be extended in the future, or the Starshot project may also fall victim to this weight calculation. Maybe while we're developing it, we'd find some way to get up to 99% the speed of light, and then we'd only have to wait 8 years for the data. But the Starshot is probably the best thought out and most backed current project for interstellar travel, the most serious one. But it's so much more difficult than going to Mars or other planets, which, while an incredible technical challenge, is something of an extension to what's already been done, hopping between the different planets in our own solar system. Many technological developments need to take place before the design can be feasible. It's not something that you could just throw billions of dollars at and have built in a few years. You need to be able to keep the weight of the whole probe, including the wings, incredibly low, comparable to the weight of a smartphone nowadays. And that requires very big scalings down of modern technology, although I guess not unfeasible with things that we've seen from Moore's law and such as this. Depends what you want on your probe, depends how many of them you're going to launch, that kind of thing. Then of course you need the fleet of lasers that could accelerate the craft. You have to actually build those, you have to actually show that they can be done. You have to find a way to reliably beam all of that laser light onto a tiny sail, which will be accelerating away from you very quickly. And you have to keep it focused, presumably, on the dead centre of the probe so it stops spinning. You need to keep the irradiation uniform so that you can get a proper acceleration forward for the probe. And this is an incredible optical challenge. It's even been mentioned and considered that some unscrupulous person might launch a giant mirror into space to try and reflect the beams back down. And when your science project could be turned into a giant death ray, that's when you know you're really dreaming. And once you get into space, you might even have to contend with space debris. If you're travelling at 10% the speed of light, from your perspective, space debris is coming at you at 10% the speed of light, and that's enough to ruin anyone's day, and potentially smash up your probe if you get unlucky. That's why most plans involve sending a huge fleet. You can afford to lose most of them as long as a few get lucky and survive, and you don't need to invest in any heavy, expensive, not yet technologically developed shielding to worry about protecting them too much if they do hit something. Yet the dream and the lure of interstellar travel remains strong, not just because we're discovering more and more exoplanets around nearby stars. The discovery of Proxima b, an Earth-sized planet in orbit around our nearest star, led to considerable hype in the scientific literature and in the media. Scientists disagree, however, about whether it could be habitable or whether such a planet, formed in the way that we think this Proxima b planet did, would lose its atmosphere far too quickly for life to develop. Breakthrough Starshot, though, is an exciting project to follow, especially because of the many technologies that it requires are likely being developed for different purposes. Miniaturization of computers, better lasers. You can see that people have alternative motivations for developing this that doesn't necessarily rely on some brand new technology that's solely designed for interstellar travel. The same cannot be said for many of the more exotic fuels. I mean, no one at present really has a motivation to spend billions of dollars developing a antimatter containment unit, for example. Even so, it seems a very long time before we'll truly be able to reach the stars. For now, we'll have to make do with looking at them. Thanks for listening to this episode of Physical Attraction. I don't think it'll be the last one we do on interstellar travel by a long shot, because there's an awful lot that I didn't get to. There's a lot of ideas that I didn't talk about, and there's a lot that I'd like to learn about myself and then tell you guys about. But while we're at it, Centauri Dreams is a great website that I used a lot for this episode. They detail all of the different kinds of ways that people have considered trying to get interstellar travel to work. They have all kinds of information about technical aspects of the Starshot project, news, developments, and so on. Probably everything I've said is already obsolete by the time you hear this episode, so go and check it out and see what they've come up with. Now the usual set of plugs. You can talk to us on our website at www.physicspodcast.com. You can follow us on Twitter at PhysicsPod. We have a Facebook page, Physical Attraction. You can listen to our sister podcast, which is all about historical dictators. It's called Autocracy Now. If you search for Autocracy Now, it comes up on Google. I tried it. Or you can go to autocracynow.libsyn.com. And if you want to support what we do, there's several good ways of doing that. One of them would be, of course, to donate to the show via Physics Podcast. You can find the PayPal link, the Patreon, you can buy a bonus episode. But of course, the thing we really like you guys to do is to tell your friends and your podcast listening enthusiasts in your life to listen to the show, because they'd be little helps. Until next time, take care.